Matter, phases, and classification. We could generally define matter as anything that has both mass and volume. Now, don't forget mass and weight are different things. Weight depends on the pull of gravity, so you can weigh something different on the moon than you do on Earth, but mass would be the same in both places. So if it has both, then we can call it matter. Matter would come in different phases or states, such as what's shown here. We've got the solid, the liquid, and the gas phase. Solid, as defined here, has a fixed shape and a volume. So you see this little cube of matter sitting down in the bottom of the flask. It doesn't stretch out, and its shape stays the same, so it's fixed both. Whereas in the liquid state, the volume remains constant, but the shape conforms to the container. I pour it into a different shaped container, it's going to take that shape, but the volume of it would be constant. In the gas state, neither one's constant. It's going to fill to make maximum use of that entire space, that entire volume inside the container, and of course take the shape of it. Now on the molecular level, it's being a little bit different, and the PhET simulation here does a nice job of showing that. Here we're simulating some neon atoms in the solid state, and you can see their shape is remaining the same. They are wiggling, they do have some vibrations, but they're not moving out of that crystalline structure. If we compare that to the liquid state, here it's like you poured a little bit in. As you can see, it's starting to assume the shape of the bottom of that container as it spreads out. The molecules are moving a little faster, but they can slide past each other now as well. It's not holding its own shape, but it is holding the volume. And you see occasionally you get a couple like these guys here, which get enough kinetic energy to actually break away and go up and start to evaporate. And that's why water and other solvents will dry out over time as slowly the molecules break away. Now if we go over here to the gas state, now we got all those molecules that are just filling the entire space available to them. They're moving faster. There's lots of empty space between them. Okay. The law of conservation of matter says that right there says that in a chemical reaction or a change like that, you're not going to create or destroy the matter. So if I start off with 5 grams, I better end up with 5 grams at the end. For example, we have this bottle. It's got pre-beer, as they say in here. So it's got some mixture in the bottom, some sugar. It's probably got some yeast in there. You let it ferment for a month or so, and it turns into beer. What else is in there? Carbonation. You got the bubbles and the fizzes. Down here, you've got the ethanol, the actual alcohol that's produced. But if I weighed it, it would weigh exactly the same amount because, again, nothing's been created or destroyed, just changed the format. And so that's a law that everything we do in chemistry we're going to have to follow. All right, now atoms, molecules, elements, compounds. What's the difference is they're all different ways that we can describe matter and how it kind of comes together. Of course, atoms are the smallest non-divisible chunk of matter. That is, without doing nuclear reactions anyway. And so I could have an atom of hydrogen, an atom of helium, an atom of carbon, that sort of a thing. Some substances do show up as single atoms. Iron is very often just a single iron atom, for example, or calcium, or that kind of a thing. Other ones, they might come in pairs, or 3s, or 4s, or something like that. So in this figure here, we see hydrogen gas, and you see there's 2 atoms stuck together. So here's a hydrogen molecule, here's another hydrogen, here's another, and they're always paired. Same thing with oxygen gas. Phosphorus turns out to come out as 4 atoms stuck together, or sulfur actually 8. So there's lots of different variations out there. As long as the atoms, though, within each one of these is the same type, it's considered an element. And of course, all of the elements that are out there are shown on a periodic table, such as this one here, where you got hydrogen, lithium, beryllium. Here's over here carbon and nitrogen, and we'll be doing a whole lot more of that. But that's why this is called the periodic table of the elements. All right. Because I have more than one atom here, they are not just simple atoms anymore. Now we're going to call them molecules. And again, if the molecules have all the same type of atoms, then those are still elements, right? But they do come as molecules. On the other side here, we have different types of atoms that are making up those molecules. So water, for example, H2O, 2 hydrogens and 1 oxygen. It's different types of atoms, but they're still stuck together. That whole thing is a molecule. but it's not an element. Carbon dioxide, CO2, 1 carbon and 2 oxygens. Here's glucose, or blood sugar, C6H12O6. All good examples of molecules. So make sure you know the difference between those definitions and be able to classify those matters. Now, usually when we find atoms, molecules, and such out in nature, they're not in pure form. Once in a while you can find it that way, but usually they're contaminated or they're mixed with something else. Very rarely do you actually get a pure substance. Now, we can do that in the lab or industrial processes. We can purify things, right? But most things in life are mixtures. And so the technical definition here of a mixture would simply be something that has 2 or more types of matter. Maybe it's water mixed with oxygen. Sounds like a good place for fish to live, right? Just like a bucket of blue and red marbles all mixed together, well, that's how mixtures would be too. So if I'm trying to classify matter in general, I'm going to have a chart sort of like this, where I can start off with matter, and I can ask, first of all, is it pure or is it a mixture? Pure substances, again, only one type here, at least 2 or more. Now, we already talked about how we can further classify these pure ones as either elements or compounds, and again, that's just based on, are there only a single type of atom involved, or are there multiple types of atoms, elements versus compounds. Mixtures we can also subdivide into either a heterogeneous or a homogeneous mixture. Homogeneous meaning the same throughout, or hetero meaning different throughout. So if I look at a sample of that mixture, is it the same no matter where I look? The top of the jar, the bottom of the jar, somewhere in the middle. No matter where I look, is it the same? If it is, well, that's a homogeneous mixture. And the book uses a sports drink as an example. Lots of different types of atoms, molecules, compounds in a sports drink, but still, if I look anywhere at the top or the bottom of that, I'm going to pretty much find the same thing. It's homogeneous all the way throughout. Where a heterogeneous, the book uses salad dressing as an example. Wherever I look, I might see something a little different. A chunk of a herb somewhere. If I look at the top, I might get a layer of oil. At the bottom, I might get some solids precipitating out. So that's definitely a heterogeneous mixture. Different depending on where I look. Well, one thing about, one way to classify, I guess, compounds would be the fact that you can break them up into the different atoms that make them up through chemical reactions or some type of a chemical change. So the book uses this as a great example. Water. You shoot electricity through water. It actually breaks that water up into the hydrogen and the oxygen. Now, hydrogen, when it comes off as a pair, 2 hydrogen atoms stuck together, and oxygen comes off as a pair as well, 2 oxygens stuck together. And so here we got this beaker of water, an electricity source. They put a couple test tubes to collect the gas as it comes out, and water is being transformed into that hydrogen and oxygen. Now, if I start off with, again, 5 grams of water, then I'm going to get a total of 5 grams of hydrogen plus oxygen when I add up the whole thing.